Okay, here I'm going to present another method, more general than undetermined coefficients, for finding a particular solution of a non-homogeneous differential equation. So I'm going to focus on the ones that take the form y double prime plus p of xy prime plus q of xy equals, okay, so it's non-homogeneous, so it's going to equal some other function. Okay, so it's going to depend on us knowing the general solution to the associated homogeneous differential equation. So suppose that the general solution to this right here is yc equals c1 times y1 of x plus c2 times y2 of x. All right, then we know that y1 and y2 are linearly independent. Then a particular solution to the non-homogeneous case, where I have some driving function f of x on the right, is given by this big complicated looking expression. Okay, and so we'll see in class exactly where this comes from, but right now we'll see how to use it in this video here, in particular just focusing on how to use this. So yp is equal to, we take one of these two functions here, we call them y1, and the other y2. So negative y1 of x times the integral of the other function y2 times this function f of x over w of x dx plus the other guy, so basically we switch them around, so plus y2 of x times the integral of y1 of x, f of x, w of x dx. Okay, so where this w is the Wronskian of y1 and y2, which is simply equal to y1 times y2 prime minus y2 times y1 prime. So this actually comes about from assuming a particular form of a particular solution and then deriving what it actually would have to look like. Okay, and so that again, that's where these come from. All right, so you can see here that since we're integrating, since we have these indefinite integrals, we will have integration constants, but we can take those to be 0. Okay, all right, so let's do an example. All right, so we will find the general solution to this non-homogeneous differential equation here. All right, so first we have to actually know, if you remember up here, we have to know what yc is. We have to know what the solution to the associated homogeneous differential equation is. So we have, we'll get our characteristic equation, so r squared minus 2r plus 1, which is equal to r minus 1 squared. That's equal to 0, which means that r1 equals r2 equals 1 is going to be the solution. So we know, therefore, that y sub c will equal some c1 e to the x plus c2x e to the x. Okay, so again, so first we find our y sub c, then we call one of these y1, so I'll call that one y1, and the other one we call y2. All right, so here you see in the formula we need to know what w of x is for both. So let's just go ahead and find w of x next. Okay, so we need y1, so remember w of x is going to be equal to y1 times y2 prime minus y2 times y1 prime. So we can find y1 prime is just the derivative of e to the x, so that's e to the x. Then y2 prime is the derivative of x e to the x. So we have to use the product rule on that. So the derivative of x is 1, so 1 times e to the x, plus x times the derivative of e to the x, which is just e to the x. All right, so therefore w of x will equal y1 e to the x times y2 prime minus y2, which is x e to the x, times y1 prime. So if we distribute here, we'll see we get e to the 2x, so e to the x, that's e to the 2x, then plus, plus x e to the x times e to the x, so x e to the 2x, minus x e to the 2x, so that's just equal to e to the 2x. Okay, so that's what the denominator is going to be in both of our integrals. All right, So let's recall again what the integrals are. So we're going to need to integrate y2 f of x over w of x. So let's do that. So scrolling up here, y2 is x e to the x. Then the function, this guy right here, e to the x over x. And then divided by w of x dx. Okay, so we see we've got some canceling going on here. So this x will cancel out with that x. And then e to the x times e to the x in the numerator is just e to the 2x. So that's going to cancel out with that denominator. So this simply becomes the integral of dx. And that's just equal to x. So remember that we can take the constant of integration to be 0, so we get just x out of that. All right, so now we have to do the other one. So now we need the integral of y1 f of x over w of x dx. So that's going to be the integral of y1 is e to the x. You'll remember that f of x is e to the x over x, and w of x is e to the 2x. So if you simplify this out, then these e to the x, that's e to the 2x again. So it's going to cancel out with the e to the 2x in the bottom. And so this is going to become the integral of 1 over x, because of that guy right there, dx. So again, taking the constant of integration to be 0, we get natural log of the absolute value of x. All right, so now we're ready to write down a particular solution. So yp, we do negative y1 times the integral that had y2. So negative e to the x times the integral that had y2, which is x, then plus y2 times the integral that had y1. And y2 is x e to the x times the integral that had y2. Okay, and so now if you remember that the solution to the non-homogeneous case is y equals yc plus yp, so that's going to be equal to c1 e to the x plus c2 x e to the x plus this bit right here. Okay, so if I rewrite this, then you see what I have here is c1 e to the x plus c2 x e to the x minus x e to the x plus x e to the x natural log absolute value of x, but we can combine these two. So if we factor out an x e to the x, we get c2 minus 1. So we can simply call that another constant. So we would rather not just have things being repeated like that. So that's just some other constant, c3. So in our most simplified form, our general solution is y equals c1 e to the x plus c3 x e to the x plus this bit here, x e to the x natural log absolute value of x. All right, I'm going to give you one to try. Actually, before I do, let me point out something. So, you know, this always works, unlike the method of undetermined coefficients. But depending on what these two integrands are, it could be a really tricky method. Okay? All right, so find the general solution here to y double prime plus 4y equals 3 times the cosecant of x. Okay, so you'll notice that cosecant of x, that's not a candidate for our undetermined coefficients either. So we would use variation of parameters. All right, press pause while you work on this. Okay, so first up, you should have gotten that the characteristic equation is r squared plus 4 equals 0. So we have r squared is negative 4, or r is plus or minus 2i. So we put that into the form for complex roots, or non-real roots, then we get yc equals c1 cosine of 2x plus c2 sine of 2x. All right, next up we find the Wronskian, w of x. Right, so we can call the first one y1, the second one y2. So we have cosine of 2x times the derivative of sine of 2x minus sine of 2x times the derivative of cosine of 2x. So we get cosine of 2x times 2 cosine 2x minus sine 2x times negative 2 sine 2x. And then we clean that up. And if we factor out a 2 here, we'll get cosine squared of 2x plus sine squared of 2x. So that's just going to be equal to 2. Okay, so in this case, our Wronskian is just 2. All right, so next up we find our two integrals. All right, so for the first one, we get the integral of y2 times f over w dx. So we just substitute all those functions in. And we're going to clean this up here by writing cosecant of x as 1 over sine of x. And we'll use the identity that sine of 2x is 2 sine x cosine x. All right, so then we get these 2's here cancel. The sine of x cancels. And we get 3 cosine of x. All right, so our first integral ends up being 3 sine of x. All right, so we'll work on the second one now. All right, so this integral is actually going to be a little trickier. So what we're going to do, again, we'll use that the cosecant of x is 1 over sine of x. And we'll use an identity, and since this is 1 over sine of x, so since this trig part has just sine, I'm going to use the identity for cosine of 2x that has just sine. And that's that cosine of 2x is 1 minus 2 sine squared of x. And I'll pull the 3/2 out front. All right, so that's what that looks like. So we distribute the 1 over sine of x into the 1, and that's going to give us cosecant of x. And then we just distribute it to the second term, so that's going to be minus 2 times sine of x, and all with respect to x. Right? So the integral of cosecant of x is actually worth memorizing, same with the secant of x. So I'll actually derive it for you in the end if you don't already know, for those of you who don't already know how to get it. But for now, I'm just going to go ahead and write down what the answer is. So this is going to equal 3/2. All right, so the integral of cosecant of x, so 3/2 times this whole thing, is going to be the natural log of the absolute value of cosecant of x minus cotangent of x. And then minus the integral of 2 sine of x, so that's going to be plus 2 cosine of x. And then again, we have our constant of integration equal to 0. So finally, we just need to distribute the 3/2. All right, so now we're ready to put it together for yp. So first off, we have the integral that had the y2 in it, which is 3 sine of x, gets multiplied by y1, which is cosine of 2x. Sorry, it gets multiplied by negative y1, which is cosine of 2x. Then plus y2, which is sine of 2x. times the integral that had y1. So that's all of this. All right, so that's our yp. And we'll clean it up a little bit. So distributing the sine of 2x and just cleaning up the first, we get this. But now we're going to be able to actually simplify these two pieces. So we can use the difference identity for sine. So if we group them together and pull out the 3, we get sine 2x cosine x minus sine x cosine 2x. And this right here is simply the sine of 2x minus x, which is equal to the sine of x. Okay, so we can now write our cleanest version of y sub. All right, then finally, to get the general solution of the whole differential equation, we have to add our y sub c to that. Okay, so simply add y sub c to that, and we'll have our answer. All right, so here's our solution. All right, so as I said, I will show you now how to integrate cosecant of x dx. So as a quick reminder, the derivative of cosecant of x is negative cosecant cotangent. And the derivative of cotangent of x is negative cosecant squared of x. Right? So the trick to integrating this, and the one for secant is similar, is to create a fraction and multiply the top and the bottom by cosecant of x minus cotangent of x. All right, then if we distribute in the top, we get cosecant squared of x minus cosecant x cotangent x. And some of you probably see it already, but I'll go ahead and do a u substitution just to show it all out. So now I'll do a u substitution for the denominator. So then I get du will be equal to the derivative of cosecant. Just reminded you guys of those. So that's going to be negative cosecant x cotangent x minus the derivative of cotangent, which is negative cosecant squared of x. So that's equal to negative times a negative, that's going to be positive, so that's going to be simply cosecant squared of x minus cosecant x cotangent of x dx, which is precisely our numerator here. All right, so with a u substitution becomes the integral of 1 over u du. So that's natural log absolute value of u. I'll just leave off the coefficient of integration right now, since I said you were specifically doing this for variation of parameters. And so that becomes the natural log absolute value of cosecant x minus cotangent x. Okay, again, worth memorizing for that one. All right, so as I said earlier, the tricky part of these is the integration. And I think that this last example shows you that.